assuming the integrand exists, right? So let me just assume that this is equal to y. Okay? So if this is equal to y, so y squared becomes no more square root out here. So just 1 plus x times, this is still y, right? 1 plus x times y. Now, we treat x as constant, treat y as an unknown, solving for the quadratic equation. X minus 1, right? Y plus minus square root of b squared minus 4ac. Cannot be minus, right? Has to be positive, right? Y has to be positive, right? So this is fine. So it looks like, well, it's really a function that we're familiar with. So this is easy to solve. Just solve this integral. Half x plus x squared plus 4. Yeah. So this is just easily 0 to 1, half x dx, 0 to 1, half square root of x squared plus 4 dx. Okay. This is just x squared over 4, 0 to 1 plus. So to solve this, or hyperbolic substitution, now once I let x equal to 2 times sinh of t, then dx is 2 times cos of t. This is similar to the trigonometry, right? dt. And the inside integrand now is just 4 times sinh squared plus 4. 4 taken out, square root of 4, 2 and 2 cancel out. Square root of sinh squared plus 1. Cos square, square root of cos. This is also, this is a little different. Trigonometry, we have 1 minus sine square equal cosine square, but this is plus equal cos square, right? Cos square, cos. So this is easy. Also, don't forget, change the boundaries. Right? So again, let me just recall. Sinh is half of e to the t minus e to the negative t. When x is equal to 0, sinh is equal to 0. That's when t is equal to 0 also. Because 1 minus e to the 0, 1 minus 1 equals to 0. No problem. Starting from 0. But when x is equal to 1, 2 times sinh equal to 1, sinh equal to half. When does that happen? Well, that's just e to the t minus e to the negative t equal to 1. Okay, multiply e to the t on both sides. E to the 2t minus 1 equal e to the t. E to the t square, this one, minus e to the t minus 1 equals 0. I solve for this quadratic. Okay, so this just becomes e to the t half plus minus square root of b square root of 5 has to be plus. This has to be positive. Right? There's no problem. So t is equal to log half. Right, this, no problem. Log square root of 5. So integrand is this. Dx is that. So altogether, 2 times cos square t dt. Okay. So again, we recall. Right? We recall the meaning of cos. Right? Cos half e to the t plus e to the negative t. So obviously, cos square equal to 4 e to 2t plus 2 plus e to the negative 2t. Right? So obviously 2 times cos square equal to half. Right? So this should be easy. 1/4 plus 0 log half 1 plus 5. Half is 2t plus 2 plus e to the negative 2 dt. Okay, so this is just some standard integration. As I pulled out half here. So the rest is just antiderivative. Half e to the 2t plus 2t. This is what? Negative half e to the negative 2t. 0 log square root of 5. But the question is, what is exactly e to the 2t? E to the 2 times log. So t equals log half. Right? So this, to put the 2 on top. Right? E to the right, 2 becomes this power. So e to 1 plus square. And also, what is e to the negative 2t? Right? That's something I believe it's going to be interesting. So e to the negative 2t, e to the negative 2 log e to the log 1 plus power negative 2 half power negative 2. Right. So this looks like it's reciprocal. Right? But this I can multiply by its conjugate. Right? Square root of 5 minus 1. So 5 minus 1, 4. 4, 2, half. Square root of 5 minus 1. All together, no problem. So this is just to, in order to be the same form as this one. So therefore we can simplify. Half times e to the half. Okay, half times this. 2 to 4, 4 times 8. 1 plus. Minus this. square root of 5 minus 1. 1 minus square root of 5. Same thing. Plus log 0 goes into here, here, here. 0, half, minus half, nothing. Okay. So this is just what? I believe 4 times square root of 5 on the top over a. So half of square root of 5. Right, that's for this. Plus log. So easily this combined with this, so over 4, 1 plus square root of 5. This onto this. Log. Okay, we successfully solved for the integral. Turns out to be some constant, but like I said, the integrand turns out to be this familiar function. Right? But how do we know that this integrand, infinite series, actually converges? Right? For any fixed x that's in this closed interval. Right? So that's the most difficult part, right? Integral solving is not that difficult. So first of all, I say this whole integrand is bounded above. How do I know that? Well, if I say a1 of x, I just call it a1. a1 is 1 square root. Perhaps like this. a2, 2 square roots, x times square root, a times, 2 square roots. a3, 3 square roots, x squared, 1 times x times square root. n square roots, n roots. So as n approaches infinity, how do we know that the series sequence actually converges? Right? First of all, it's bounded above. The reason is because I can say for A3 can be written like this. X square root 1 plus x. I say it's less than or equal to 1 plus 2x plus x squared. Right? On top of 1 plus x, I plus x and plus x squared. Right? So this is enlarged on the right-hand side. So this is a perfect square. Square rooted 1 plus x. Right? So 1 plus x times square root of 1 plus x times 1 plus x, right? This becomes 1 plus x. No problem. Now we have 2 roots. Still plus x times 1 plus x squared. Right? But this is no larger than 1 plus x times 1 plus. On top of that, I plus x, so 2x plus x squared. Right? So this is further loosened because x is here. Right? So this is 1 plus x times this is again 1 plus x squared, square root, so 1 plus x. No problem. And so this is square root of 1 plus x squared, no larger than 1 plus 2x plus x squared, right? This is fine. Equal 1 plus x square root, right? No larger than 2, right? Because x is no larger than 1. Right? A3 is no larger than 2. Bigger than 0. No problem, right? So according to the same logic, for any an, right, n roots, doesn't matter, we have 3 roots, that doesn't matter. Follow the same logic, we can easily, right, bound it above. Right? It works the same way if you have 4 roots, 5 roots, n roots. Right? The same logic, right? Still bounded above. And next we want to prove that the sequence is actually increasing. Right? If it's increasing and if it's bounded above, then it's convergent. Okay, so we've proven the sequence is bounded above. Now we want to prove it's increasing. Right, so how do we, like I said, A1 has 1 root, A2 has 2 roots, A3 has 3 roots. So AN has n roots. So first, I'd like to know A2 and A1. Is A2 bigger than A1? Right? So all I have to do is to use this minus A1. Right? So that is equal to multiplied by its conjugate. Right? So that way, this plus this on its bottom. But the bottom is already positive. Right? That's fine. I'm focusing on the top. Right? So here I have, so this multiplied by its conjugate gives me this square minus this square. So this square is this. This square is this, right? Bottom, some positive number. 1 minus 1. This minus that. Right? Minus x. X common factor. Square root of 1 plus x minus 1. X already bigger than 0. This is bigger than 1. This is bigger than 0. X bigger than 0. Bigger than 0. Right? So A2 really bigger than A1. Okay, so far I've proven A2 is bigger than A1. Okay, now we use mathematical induction. Okay, we can assume now AK bigger than AK minus 1. Now we want to prove AK plus 1 bigger than AK. Right? So AN means we have n roots. Right? Likewise, so this minus that equals what? Right? That is equal to 1 plus k plus 1 roots minus 1 plus k roots, right? So what is that equal to? Again, I multiply its conjugate, right? So meaning multiply this plus that, right? Appears on the bottom first, but already positive number, so don't care, right? Focus on the top. Top is this multiplied by its conjugate. So this square minus this square. So 1 minus this, right? So here we have k plus 1 roots. After this root is gone, here I have k roots. Likewise, here I have k minus 1 roots. No problem, yeah? Which means, so 1 minus 1 gone, right? So this minus this, but still x is a common factor. So this is has k roots, which means must be equal to ak. Like I said, how many roots are the same subscript, right? So ak, and so this is ak minus 1. Bottom is positive, x is positive. This is, we assume this is bigger than that, so positive. So really, this, so yes, no problem. Yeah. So according to mathematical induction, an is really increasing, right? And also we've shown that an is really bounded. Below by 0, bounded above by 2, so no problem. It is really convergent, right? Convergent to this for any fixed x in this